This is the first of two videos that examine how to calculate and interpret an effect size in a two independent samples t-test. In this video, we introduce the concept and need for effect sizes and how they differ from test statistics such as the t-score. Once you've completed your study and hopefully found a statistically significant effect, the next natural question is, well, was it a big effect? Was it a small effect? Just how big is the effect? Now, sometimes answering that can be pretty straightforward. Think back to our two independent sample t-test example, where we found that 7-year-old children with hearing loss who had been diagnosed by 3 months of age had expressive language scores that were 11.20 months higher than those who'd been diagnosed later than 3 months of age. Language skills that are 11.20 months, nearly a year higher, is pretty straightforward and has some inherent understandable meaning to people. But unfortunately, often the results just don't lend themselves to an easy-to-interpret value. For example, let's say we conducted a study looking at whether there was a difference in self-confidence for adolescents based on whether or not they took part in a sport. We're not actually going to calculate our t-score, etc., so we'll just do an abbreviated summary here. Let's say we have two samples, one containing high school students involved in sports and the other containing high school students not involved in sports. We then assess their levels of self-confidence using the Mason Self-Confidence Scale and find that the mean self-confidence rating for youth involved in a sport was 83, but it was only 73 for those not involved in sports. So scores are 10 points higher for youth who are involved in a sport. Great, but what does 10 points mean? How do you interpret that? It really has no inherent meaning on its own. How do you make sense whether this is a big difference or a small one? Now, answering this gets a little tricky and can throw some people off, so follow along closely. Let's also say that we obtained a huge t-score, making our p-value tiny, and we easily rejected the null hypothesis. Does that mean that the effect of playing a sport is huge? Well, actually, no, it doesn't. The t-score and p-value indicate that the effect is statistically large, meaning that it's statistically unlikely to have happened if the null hypothesis is true. But it really doesn't tell you the actual meaningful real-world size of the effect. Now, to see what I'm talking about, let's take a quick look at the TScore formula for a two independent samples t-test. Our t-score is the difference between our two sample means, that's how large of an effect that we observed, divided by the standard error of the difference in means. The standard error indicates how large of a difference we expect to see between sample means given our sample size and the variability in our samples. In essence, the value of our t indicates how large the difference is in standard errors. This is how we test whether the means of the two populations are different. But think back to our video on sampling distribution of the means and standard errors, and how the standard error gets smaller as the sample size gets larger. Here we see that same principle mathematically in the formula for the standard error of the difference between means. Because the sample size shows up in the denominator of the standard error formulas, larger samples will, all things being equal, have smaller standard errors. Now, smaller standard errors mean larger t-scores. This is a good thing in that larger t-scores make it easier to detect differences in our population means. Now, this is really important. The t-score is based on some effect, in this case, the difference between our two sample means divided by the standard error. As the sample size gets larger, it's not that the effect is getting larger. If the average in one population is 10 points higher than the average in the other population, those averages don't change just because the samples get larger. On average, the difference in the population means that we're sampling doesn't change. What's changing is the standard error gets smaller. As our sample sizes increase, the standard error gets smaller and smaller, and t gets bigger and bigger. But the actual effect stays the same. It just looks larger statistically because we're evaluating it using a smaller and smaller yardstick that makes it look bigger in a statistical sense. In a way, you can think of a larger sample size as some sort of statistical microscope that zooms in on our data and allows us to see smaller and smaller effects more clearly. That allows us to better recognize and understand small effects in order to know what's real and what's actually just some blurry noise in the data. In the end, from the perspective of a t-test or any statistical test, even the smallest effect can look big and clear and very real if we have a large enough sample size. In a statistical sense, something may appear huge, but is really just a teeny tiny little thing. While that's awesome, it can also create a serious dilemma. An effect that is actually very small may look very large statistically. A small difference in means that's examined using huge samples can end up giving you a very large t-score and a very small p-value. But the actual difference is just tiny. The actual effect may be small, but our large N allows us to zoom in and see it more clearly and know that it's there and know that it's real in the same way that a powerful microscope lets you zoom in and see that tiny little water bear in all of its glory. Now, let me share a story with you. Years ago, many years ago, a former professor of mine got into a scholarly scuffle with an academic rival over research on family size and child intelligence. In a nutshell, his rival published research that, to put it crudely, argued that larger families had dumber kids. My professor countered, in part, by arguing that this work was often based on samples that were huge, and the actual size of the effect was small enough to have no practical value or impact. For example, if you need a gigantic family in order to have a tiny difference on child intelligence, who cares? Now, I personally do a lot of work in epidemiology, and it's a common issue that we have to address. Huge population-based samples can find small effects that are significant, but small enough to have little actual relevance in the real world. There's a saying that everything is significant if your sample is large enough. So, what do we do? Well, the solution is to also report what is known as an effect size. An effect size describes the actual magnitude of a difference or effect, rather than its statistical significance. Now, there are lots of different ways of measuring an effect size, but the key is that they describe the effect that we see, but are not influenced by how large or small the sample is. Consequently, they do give us an idea of just how large something is in a real-world sense, but they don't tell us how likely it is that whatever we're talking about is real or just some random variation. But that's okay. That's not the job of an effect size. One widely used ways of calculating an effect size is to divide the effect that you observed by the standard deviation. In the case of the two-sample t-test, that's simply the difference in our means divided by the pooled standard deviation. In other words, how big of a difference did we observe in terms of standard deviations? Now note again that we're talking about standard deviations, not the standard error. Remember, the standard error tells us how spread out we expect sample averages to be, in part based on how large those samples are. But the standard deviation tells us how spread out the original individual scores are, and it's not impacted by the sample size. So our effect size indicates how large of a difference there is between our two population means in terms of standard deviations. Now, it might help to visualize this. So let's say that we sample from two populations and determine our means and the pooled standard deviation. We then calculate our effect size, and it turns out that the effect size is equal to 0. What does that suggest about our two populations? Well, it tells us that we think there is no difference between our two population means. If we made a graph of the theoretical distribution of scores based on our estimates of the two population means and the pooled standard deviation, the two distributions would completely overlap each other. But what if we did find a difference? What if our effect size was 0.20, indicating that the difference between our two means was equal to 0.2 standard deviations? What would that suggest about the distribution of scores in our population? That suggests that if we graph the distribution of scores for both populations, the difference between the means would be equal to 0.20 standard deviations. What about if our effect size was 0.5? What would that look like? In that case, the difference between the means would now be equal to 0.50 standard deviations. They're definitely getting further apart, reflecting a larger difference or a larger effect. What if the effect size was 0.80? The difference between the means would then be equal to 0.80 standard deviations. The two means are even further apart, reflecting an even larger difference or effect. Now, this specific effect size, the difference between means divided by the standard deviation, is often called Cohen's d after Jacob Cohen, who first really popularized it. But there's some ambiguity in that there are different variations based on exactly how you calculate the standard deviation. Is it pooled or not pooled? If you pool it, exactly how do you pool it? Do you in fact know sigma? So in practice, the label Cohen's d is sometimes applied to a variety of subtly different formulae that all get at the difference between the means divided by some standard deviation. In this case, technically, because the specific formula we're using is based on our inferential equation for the variance with n-1 in the denominator, and because we're using the pooled standard deviation, in which case each sample is weighted by its sample size, this is what's known as Hedges G, proposed by Larry Hedges, who, on a side note, in 2018 won the Chidan Prize for Educational Research for million. Yeah, I'd be smiling too. Before moving on, I should also note that, like he did for correlation coefficients, Cohen proposed some widely used labels for different sizes of this general type of measure. Specifically, he suggested that an effect size of 0.20 was small, while an effect size of 0.50 was medium, and an effect size of 0.80 was large. Now, while they're widely used by researchers, don't fall into the trap of just relying on these labels of small, medium, and large. There's more to consider when you're evaluating how large of an effect there is. For example, let's say that you're testing a new intervention. When determining whether your effect is small or large, you probably also want to consider the effect size that has been seen in other similar interventions or with other interventions that are targeting the same outcome. Is it large relative to what other interventions can do? Okay? Now, this wraps up our discussion of the effect size at a conceptual level. In our next video, we'll go through the calculations and look at how to interpret the results. Okay? Bye for now.